just try to stay sober. It's eating you, and they say you are a monster.
This is the concept video for directional derivatives and gradients. So if you have a multivariable function, f of xy for example, and we want to find the rate of change of that function, well, before we had the partial derivatives, df dx and df dy. So if we're looking at the xy plane, then df dx showed us the rate of change as we moved in the x direction, and then df dy showed us the rate of change as we move in the y direction. But what if we want to go in some arbitrary direction? Like, let's say 45 degrees up above the x-axis, for example. Well, that's where directional derivatives come into play. So first we're going to define something called a gradient. So we use this upside down triangle, and that means the gradient. So the gradient of f of x, y is a vector df dx df dy. And if you want to write it in this form, it's like a column matrix, I guess. I don't know how your professor does it, but those are the two ways you can write it. It means the same thing. You can write it as this, using the alternate notation. So this vector, and we'll go into its properties later, but it's pretty much, let's say we have df dx, df dy. This vector is going to be the vector sum of those two. So our directional derivative, and we call it du. This is some vector of f of xy. So this is going to be in any direction, this derivative, and this is going to be a scalar quantity. So this is a vector, and d, this is just the operator right here. This u is going to be a unit vector in the direction we're going in. So like before we had df dx, so our unit vector would have been 1, 0, and going in the y direction our unit vector is 0, 1. If we're going 45 degrees, then we're going to have 1, 1 divided by the magnitude of 1, 1, which is 1, 1 over the square root of 2. So that's what u is, and f of xy is our function that we're trying to find the rate of change of, and this is going to be the dot product between the gradient vector and our unit vector. And I'm going to write this with a hat, indicating it's a unit vector. So you can write this as df dx of the x component of this plus df dy times the y component of this. And since it's a dot product, we can also write it as gradient of f xy times the magnitude of, and this is the magnitude of the gradient, times the magnitude of this unit vector times the cosine of the angle in between them. But since the magnitude of a unit vector is just 1, you can write this as magnitude of gradient f times the cosine of the angle in between the unit vector and gradient f. So we'll show some examples later of how to calculate this, but this just gives the the rate of change in the direction specified by the unit vector. So if we had theta equal 45 degrees like we wanted before, cosine of theta is square root of 2 over 2. So if we wanted to find the rate of change of 45 degrees above xy axis, or the x-axis, you just need to find the gradient, find the magnitude, and multiply by square root of 2 over 2. So now we want to find the maximum rate of change of this function. So we want to find the max value of this. Well, this is going to be at its maximum when we get the maximum value of cosine theta. Well, cosine theta is at its max when it equals 1. And theta must equal 0 degrees. So when that means that the gradient vector and the unit vector of the direction we're going in have no angle in between them, so they're pointing in the same direction. So the maximum value, maximum rate of change of f of xy is equal to the magnitude of the gradient. Okay, and the direction, so the unit vector pointing in that direction of max rate of change is in the direction of the gradient. So f of xy, it points, gradient of f of xy points in the direction of maximum rate of change. Its magnitude equals the maximum rate of change. And we'll show one more property. It's normal to level curve. Of f. So let's say we have a function looking like this, a hill. Well, all these little disks here are going to be our level curves, and the gradient vector is going to be perpendicular to these. As you can see, there's a 90-degree angle. And these are pointing straight up the hill because that's the direction of max rate of change. And yeah, we can show this by defining the position vector on the level curve. So we'll call this the level curve. So when f of xy equals some constant c, and the tangent vector, we'll say this is the position vector to this area location on a curve. Tangent vector is just dr dt, or we call it v sometimes, and dr dt equals dx dt, dy dt. dy dt. Sorry. So we know that f of xy equals c, but since this curve is parameterized with as r equals r of t equals x of t, y of t, our f is going to be in terms of t. And if, I don't know if you guys learned the chain rule for multivariable functions, but if we have w equals f of xy and x equals x of t, y equals y of t, then the derivative of w with respect to t is df dx times dx dt plus df dy times the regular derivative dy dt. So if we use this chain rule, take the derivative of both sides with respect to t, this side here is going to be df dx times dx dt plus df dy times dy dt, and derivative of a constant is just 0. But you can see that this is a dot product. We have these two, df dx comma df dy, dotted with dx dt comma dy dt, and their dot product equals 0. So dot product equals 0 when the two vectors are normal to each other or orthogonal. Or perpendicular. These mean the same thing. So if it's perpendicular to the tangent vector, then it must be normal to the curve itself. Perpendicular to the curve. So that's all I want to say about these.